Black holes have long captivated scientists and space enthusiasts alike. But what if I told you that two major black hole theories, some of the most debated in modern astrophysics, just received their most compelling confirmation yet? And this news comes wrapped inside the clearest gravitational wave signal ever detected. Buckle up, because this discovery not only answers century-old questions, but also unlocks new doors to understanding the universe. A decade after the groundbreaking first detection of gravitational waves, the global LIGO-Virgo-KAGRA Collaboration has announced something extraordinary: the observation of GW25114, a space-time ripple offering the most crystal-clear data yet about black holes and the core rules that govern our cosmos. This signal wasn't just a faint cosmic whisper, it was a cosmic shout. So what exactly did scientists confirm? First, Stephen Hawking's bold 1971 prediction that when two black holes come crashing together, the resulting merger's event horizon area must be larger than the sum of the two originals. That is, black holes never shrink in this respect. They always grow. Picture two enormous soap bubbles merging. The surface area of the single new bubble is always bigger than the combined area of the two smaller ones. For decades, researchers have wondered if nature truly enforced this rule. And now, thanks to GW250114's remarkable clarity, a whopping signal-to-noise ratio of 80, they have their answer. But here's where it gets controversial. The data also upholds the Kerr nature of black holes, a concept that transforms our understanding of how space and time behave near these cosmic giants. Back in 1963, New Zealand mathematician Roy Kerr developed breakthrough equations showing that spinning black holes twist the fabric of space-time itself. Imagine light traveling around a whirlpool. Looping so many times, it produces multiple shadows of the same object. Skeptics have questioned for years whether these strange predictions really match reality. Now, for the first time, scientists have clearly detected two distinct tones in the aftermath of the black hole collision, just as Kerr's equations forecast. Let's put this into perspective with some real numbers. This jaw-dropping event was picked up by the United States LIGO, Laser Interferometer Gravitational Wave Observatory. Twin detectors, working seamlessly with Virgo in Italy and KAGRA in Japan, as a global black hole hunting trio. GW250114 came from the collision of two black holes, each about 32 times heavier than our Sun. The combined surface area before the smash-up was roughly equal to the landmass of the United Kingdom, about 240,000 square kilometers. But after merging, it expanded to nearly 400,000 square kilometers, the approximate size of Sweden. This isn't just cosmic trivia. It's a precise measurement that supports Hawking's legendary area law. For those new to black hole physics, here's why all this matters. In the 1970s, Hawking, together with physicist Jacob Bekenstein, discovered that a black hole's surface area connects directly to its entropy, a measure of disorder. This opened a whole new chapter in efforts to bridge Einstein's theory of general relativity with quantum mechanics, which seemed to follow totally different rules about reality. The ring-down phase, when the newly formed black hole vibrates and settles down, produces distinct gravitational wave signals, almost like listening to a bell that's been struck. According to Kerr, only two things determine the voice of this ringing black hole: its mass and its spin. That's not true for ordinary stars, which need many more facts to describe them fully. This, some argue, is what makes black holes so unique. And the data from GW250114 has now given the theory its boldest experimental confirmation yet. Dr. Geraint Pratten, a University of Birmingham physicist, summed it up with awe. GW250114 is the loudest gravitational wave event we have ever detected. It turned a whisper into a shout. His team, among others, could now rigorously put Einstein's and Hawking's predictions to the test. And the universe didn't disappoint. But here's the part most people miss. The technological leaps over the past decade mean we're not just verifying theories. We're entering an era of precision astronomy using gravitational waves, probing deep mysteries of cosmic evolution with unprecedented accuracy. Patricia Schmidt, who co-chairs the LVK analysis team, pointedly notes that this discovery, coming only 10 years after the historic first detection in 2015, demonstrates just how far our instruments and models have come. Amit Singh Ubi, who contributed to building this advanced technology, underscores that the exceptional clarity of GW25114 allows us to study black hole evolution more precisely than ever before. It's a testament to collective ingenuity. Of course, such bold claims invite debate. Does this definitive evidence mean other alternative theories about black holes are now less likely? Could there be unknown effects or exceptions lurking somewhere out there? And most intriguingly, does this bring us any closer to uniting Einstein's elegant relativity with the wild world of quantum physics? Or are we still searching for the ultimate theory of everything? So, what do you think? Is the evidence now clear enough to settle the debates around Hawking's area law and Kerr's spinning black holes? Or do you see room for skepticism? Do you believe future discoveries could yet challenge what we've learned from GW25114? Let's spark a conversation. Share your thoughts, agreements, or boldest disagreements.